In this video, we shall look at differential equations with constant coefficients. We shall concentrate on second-order differential equations. The general form of such an equation is as follows. d2y plus a constant a dy plus a constant b y equals to 0. The capital D stands for d dx, the differential operator. We shall find the complementary function to this equation because it is indeed the general solution of this equation. In order to get the complementary function, we first put or substitute y equals e to the power lambda x, where lambda is a constant. When we substitute this into that equation, we get the following result. E to the power lambda x times lambda squared plus a lambda plus b equals to 0. Note that this is our assumed solution to this equation, and now using this equation we can find the value of lambda. From this line, the value of lambda can be obtained by solving that equation. It is known as the auxiliary equation. It is indeed a quadratic equation in lambda. The roots can be written as, let's say, lambda 1 and lambda 2, and they are simply half a plus minus square root 1 over 4a squared minus b. This plus sign will give you one lambda, and the negative sign will give you the other lambda. There are now three cases to be noticed. Case 1 is when a squared is greater than 4b. And as you can see from this expression, if this is the case, the two lambdas, lambda 1 and lambda 2, will be real and different. In this case, the general solution to this differential equation will look like this. Y equals an arbitrary constant a, e, lambda 1x plus another arbitrary constant b, e, lambda 2x. The second case is when a squared is less than 4b. If that's the case, the term under the radical sign is negative, and we can write lambda 1 and lambda 2 as minus half a plus minus I square root b minus 1 over 4a squared, where I is square root of minus 1. For this case, the general solution to this equation will be in the following form. It's e to the power minus half ax times an arbitrary constant c cosine of this term here. Let's call it beta. So it's beta x plus another arbitrary constant d sine beta x. The third case is when a squared equals to 4b. When that is the case, this thing goes away. So immediately you see one solution is just a e minus half ax. And there is another term to this general solution, and it is given by an arbitrary constant times x times e to the power minus half ax. And this is the general solution for this case. One can also write the above in a following form, just to make it a little bit neater. E to the power minus half ax. Let's look at a few examples. The first one, we shall assume y is e to the power lambda x. Substituting this in here, we will get the auxiliary equation, which is lambda squared plus lambda minus 6 equals to 0, which can be factorized in the following form. Lambda minus 2 times lambda plus 3 equals to 0. That would give you two roots, or two values for lambda. The first value is 2, the second value is minus 3. The lambdas are real and different. So the complementary function, or the general solution to this equation, is y equals to an arbitrary constant a, e to the power 2x, plus another arbitrary constant b, e to the power minus 3x. And that's the general solution. Example 2. Again, using the following substitution, for y, we get lambda squared plus 2 lambda plus 5 equals to 0 for the auxiliary equation. Let's slightly rewrite it in a following form. Lambda plus 1 squared plus 2 squared equals to 0. That is just this equation rewritten in a slightly different form. That means lambda plus 1 is minus 4 square root, which is just plus minus 2i. And lambda is therefore plus minus 2i minus 1. So you have two values for the lambda 1 being 2i minus 1, lambda 2 being minus 2i minus 1. So they are different, but they are not real. These are complex numbers. So the general solution would take the case number 2 solution, namely e to the power minus x. The minus x comes from that number, times an arbitrary constant, let's call it c, cosine of 2x, the 2 comes from there, plus another arbitrary constant d, sine 2x. And that's the general solution. Example 3. So again, this would lead to the following auxiliary equation, namely lambda squared plus 4 lambda plus 4 equals to 0. Now when you factorize, you get lambda plus 2 squared equals to 0. And the two values of lambda are identical, namely minus 2 and minus 2. And we are looking at case number 3. So the general solution to this problem will be a plus bx, where a and b are arbitrary constant, times exponent to the power minus 2x. Example 4. First, as always, we assume the solution of that form. Substituting this in here, we get the auxiliary equation, which is 2 lambda squared minus 9 lambda plus 9 equals to 0. We can certainly factorize the above equation in the following form: 2 lambda minus 3 times lambda minus 3 equals to 0, the solution of which would give you lambda equals to 3 over 2 and 3. So these two lambdas are real and distinct or different from each other. That means the complementary function, or the general solution, is quite simply a, which is an arbitrary constant, times e to the power 3 over 2x plus another arbitrary constant, call it b, times e to the power 3x. Example 5. Again, we assume y is e to the power lambda x and put that in here. The auxiliary equation that we will end up with would be lambda squared plus lambda plus 1 equals to 0. Now that means the roots to this quadratic equation can be found in a following manner. We can try to complete the square, and that's going to be lambda plus half squared plus 3 over 4 equals to 0. That means lambda plus half squared is minus 3 over 4, or lambda plus half is plus minus I square root 3 over 2. And the two values of lambda would be, the first one is I square root 3 over 2 minus half, and the second one is minus I square root 3 over 2 minus half. As you can see, the two solutions are distinct, they are different. However, they are not real because they are complex numbers. You have an imaginary term there. That means you are dealing with case number 2, and the solution, or the general solution to this equation, or the complementary function, is e to the power minus half x, so this minus half comes from that term, times an arbitrary constant, let's call it a, cosine square root 3 over 2x. So this square root 3 over 2 comes from that part of the solution, plus another arbitrary constant b, sine square root 3 over 2x. And that's the general solution. Example number 6. First, we write down the auxiliary equation that corresponds to that differential equation. That is, by assuming y equals to e to the power lambda x, upon substituting this in here, you get the auxiliary equation. And that's going to give you lambda squared minus 6 lambda plus 9 equals to 0. We can factorize this. Lambda minus 3 lambda minus 3 equals to 0. So in this case, the two lambdas are identical. They are real, but they are identical. And this corresponds to case number 3 in our earlier discussion. That means the complementary function that gives the general solution to the above differential equation is as follows. A, which is an arbitrary constant, x plus b, which is another arbitrary constant, times e to the power 3x, where the 3 comes from the solution of the auxiliary equation. And that solves this problem. It must be mentioned that in this video we have only considered the case where the right-hand side is 0. If the right-hand side of this differential equation is a function of x, then there is an extra step involved in finding the general solution to this equation, and that step is finding the particular integral. We shall look at this case next time. As always, thank you for watching.